My name is Jeanette Quinlan. I'm with a startup that's based in San Francisco, California called Akash Systems. And we're in the communication space for satellites. So I'd like to talk to you a little bit today about communications in the space age. As many of you know, there are satellites that are orbiting above our head right now. And satellites have a couple of different purposes and a couple of different areas that help where ground infrastructure isn't able to help. So first thing that satellites are used for is broad area coverage. So this is beaming down satellite radio or satellite TV over a very, very wide area. Some satellites are actually so far out that they can see about a third of the Earth at any given time. The other area is remote area coverage. So areas where we've not been able to lay down fiber or where there aren't wireless communications that are available. So this could be places where fiber is very difficult to lay down because of the terrain or where it hasn't gotten to yet. This could also be a military base that is set up in a remote area and needs to set up very quickly and be able to communicate back home. This is also available for cruise ships and maritime and places that are too far away from ground infrastructure, as well as the internet that you get in your airplane is all coming from a satellite. Satellites are also used as a relay system. So it's actually faster sometimes to send the signal up to space and then back down to another part of the Earth than it is to go around the Earth with fiber. And there's actually satellites up in space that are relay systems for other satellites. For example, the International Space Station, instead of communicating with the Earth, it actually communicates with a satellite system called TDRS and sends the signal up to a higher orbit and then back down to space. At that higher orbit, they're able to see more of the Earth and more of the ground stations where we receive these signals. Satellites are also used for geolocation and navigation. The GPS system was actually started by the US government for military purposes, but now everybody today is benefiting from GPS satellites with the phone that you have in your hands and in your pockets. We also send pictures down from space. You might have looked at Google Earth images, or earlier this week we landed on Mars and we're sending photos of Mars back to space. So satellites are used for sending those images down and for taking those images and sending those images down. And that's why we communicate from space. I want to talk briefly about a couple of different orbits. So furthest away from home, we have Geosynchronous orbit. That is timed at that is an orbit that is far enough away that it's timed to be rotate around the Earth exactly once every 24 hours. So it stays over one particular location on Earth. With about 3 satellites, you can actually get full coverage of the Earth, which is very, very attractive. A little bit closer to home, we have what we call LEO, which is low Earth orbit. International Space Station is about 400 kilometers above the Earth. From there, it's rotating every 90 minutes around the Earth. Satellites travel at 28,000 kilometers per hour, so it's traveling very, very quickly. And in low Earth orbit, a satellite only stays over one particular part of the Earth for about 10 minutes before it's done flying overhead, and then potentially a next satellite in that orbit could follow along. At that altitude, you would need about 5,500 satellites to fully cover the Earth versus 3 that we had at geosynchronous orbit. And then somewhere in between, there's an orbit that's called MEO, or medium Earth orbit. There's not a lot of satellites there, but there are quite a few, including those GPS satellites. Back in 2010, Greg Weiler founded a company called O3b, which stands for Other 3 Billion. And the intention of that constellation was to connect the other 3 billion people in the world who were not connected. And by using this higher orbit, where every satellite rotates in about 5 hours, just under 5 hours, he was able to connect all of the world and see all of the world with just 8 satellites. And there's a slight difference in the time to communicate with all of these different orbits. So a lot of constellations that are very worried about latency will focus on the low Earth orbit. So those applications might be Skype video, it might be virtual reality. But with most of the internet traffic, about 90% of the internet traffic is now streaming, courtesy of YouTube and Netflix. So with those satellites, MEO and GEO are actually fine. You can call up your movie, and you really won't notice too much of a difference with a geosynchronous satellite than you would with fiber. So where did this all begin? Where did space communications begin? The first satellite to be launched was Sputnik I in October of 1957. And that was launched out of Baikonur, which is currently in Kazakhstan. And we're still launching astronauts to the International Space Station out of Kazakhstan today. That was not a very powerful satellite from a technology standpoint. It was actually intended to be much more complicated and much bigger. But in order to be the first to get into space, it was actually a very simple satellite that just had a constant beep. It operated at such a low frequency that it could be picked up by ham radios on the ground. So it was very powerful from a messaging standpoint. All around the world, people could tune in and hear this beep when they knew that the satellite was going to be overhead. And it was orbiting about every 90 minutes. Sputnik I only lasted 3 weeks before it ran out of battery and deorbited. But the legacy of Sputnik is really what kicked off the space race. In 1958, NASA was formed in the United States to unify the country around the mission of the space race, which would ultimately be the landing on the moon. And it's no coincidence that it was the year after Sputnik. So since Sputnik, we've launched about 4,000 satellites into space total. One of the largest communication satellites, especially in the commercial space, is ViaSat II, which was launched last year in June. This one is capable of 250 gigabits per second. It's a massive satellite, very, very powerful. And this one is located in that geosynchronous orbit where it stays over one location and orbits once every 24 hours. To build a satellite like this will cost about 400 million to 500 million US dollars. Even the lowest geosynchronous satellites today are about $250 million. And it takes about 4 years from the time that the contract is signed until the satellite is in orbit, and every satellite is designed to last for 15 years. So you have very old technology by the time that the satellite is done. So it's about 20 years. So we are taking a step back as an industry and thinking, how do we communicate from space? How do we keep up with the changing technology? These satellites that are up there weren't designed to be able to work with Netflix and YouTube and whatever else might come next. So there's a couple of trends that we're seeing in communications. The first are very large constellations. Now remember that there have only been 4,000 satellites that have been launched so far. But there are concepts out there for constellations of satellites that are even more than 4,000 satellites. OneWeb was founded in 2014, also by Greg Weiler, the same founder of O3b. And this time he wanted to focus on latency. He wanted to focus on connecting the unconnected parts of the world where they'd be able to use Skype video for chat. So he has created a 648 satellite constellation, the first of which will be launched next year out of, it'll be launched on Soyuz through Arianespace. And these satellites are actually being built at Airbus in Toulouse. He formed a joint venture with Airbus. These satellites are designed to last about 5 to 7 years before they get replenished with a much more powerful, more up-to-date satellite that is developed for where technology is going to be going. And very recently, about 2 weeks ago, SpaceX had a meeting with the FCC, and they've developed a constellation that is 350 kilometers high. It's actually even closer to the Earth than the International Space Station. But in order to do that, they need over 7,000 satellites. Now, one of the problems with satellites that are in low Earth orbit is that they spend a lot of their time over oceans or over a landmass where they can't surf. In fact, OneWeb was told recently that it wasn't able to land in Russia. So the satellites are designed to be capable over landmass where they're serving customers, but they spend a great deal of their time over the ocean or over a place where they're not making money. So while there are a couple of constellations that are in development, there are some other technologies that we're looking at. One of them is taking the advantages of those geosynchronous satellites that stay over one place and can be fully utilized all the time, but making it easier to get there. So there's a company called Astronus, which is located in Silicon Valley. They recently raised quite a bit of money from Andreessen Horowitz, which is a Silicon Valley VC, led that round. And their concept is a smaller geosynchronous bus that takes only about 1 to 2 years to build and will last about 5 to 7 years. And the cost of one of their satellites to build and launch is about 20 million to 30 million. Contrast that with almost 400 million, 500 million for some of the other larger satellites that we're seeing. There's also some very great concepts around laser communication from space. This is a very real concept that is being tested right now. We've actually demonstrated it on a mission to the moon called LADEE that had a laser communications demonstration. And laser communication is very, very powerful. You can get very, very high data rates through laser communication. One of the cons, though, is that it is susceptible to not being able to communicate when there are clouds in the sky and when there's rain. It's a concept called rain fade because of those very, very powerful connections. So sometimes you'll be over a ground station and not be able to close the link. So it's not very good for some applications where you might need to have immediate return. For example, disaster relief, where you need to take a picture and then get the data down right away. So a little bit about me. I started my career as a thermal engineer on satellites after getting my mechanical engineering degree. I've always wanted to be in space. I was inspired by the space shuttle and Sally Ride when I was a child. And what a thermal engineer does on the satellite is that they make sure that every single part of the satellite stays at the right temperature from the time that it's being built until the very last day that it's on orbit, no matter how the satellite is being used. So we have to talk to every single subsystem expert and make sure that their system is operating at the right temperature. On communication satellites, one of the biggest sources of heat and waste heat is in the communications equipment. There's traditionally something called a traveling wave tube amplifier, which is very large and clunky. And as satellites have gotten smaller and smaller and smaller, they can't fit those traveling wave tube amplifiers. And we've gone to solid-state devices, which are very similar to the ones that are in your iPhone today, or in your cell phone today. But the problem is that gallium nitride, or this very promising technology called gallium nitride, which people have been trying to put on satellites for quite a while, including myself when I was designing satellites, we were unable to get the heat out. So it would basically get way too hot. There's no air in space, so you can't put a fan on it. So I was scratching my head, looking at gallium nitride, just saying, oh, this will never work. Little did I know that just down the road from me in Santa Clara, California, there was a company called Group 4 Labs, which in 2003 started a technology of growing a synthetic diamond on the back of gallium nitride. Now, why synthetic diamond? Diamond is the most thermally conductive material on Earth, and 4 times that of silicon carbide, which is what GaN devices had been grown on before. So unbeknownst to me, this technology was being developed. About 2 years ago, I met the co-founder of Akash. Akash was founded in 2016 to bring the technology, which had been started in 2003, into the market. Once I met Felix Ejekem, who was the inventor, I knew that I needed to be a part of this company. So what our devices actually enable is the temperature on the gallium nitride to be reduced. So you can fit it on a satellite where you wouldn't have been able to before. This means that for a given power, the satellite is using smaller solar panels. And by doing that, you launch a smaller satellite, one that's cheaper to build, or you could actually keep the same power requirement and be able to serve more customers and have more radio frequency signal coming out. It also allows satellites to use the very tiny portion of the radio spectrum that they've been given and use it much more efficiently. So no matter what your satellite is, if you're going to deep space, if you're going to take pictures of the Earth, if you're going to help connect the unconnected parts of the world, you'll need to work with Akash systems. And we hope to be working with everybody who's in the ecosystem. That's what I love about the company. So thank you very much. Appreciate your time today. Are there any questions from the audience? We have a few more minutes.
Oh, we have one down there. Thank you.
I have a question. You mentioned that a satellite in its construction cost around minimum $250 to $450 million US dollars. So, and it has to be replaced in its shelf life is 4 to 5 years. So when it is so cost intensive, how it has to be managed? Is there anything being done in that direction?
Yep. So let me, thank you very much for the question. For the very, very large satellites like ViaSat II, those are about 400 million to 500 million. Those actually last 15 years on orbit. So they do make a return on investment, but it does mean that the average company can't join in that. That's really, really a high capital cost. There is a revolution on smaller satellites. So in the OneWeb constellation, it's a very, very big constellation, but every satellite is targeted to be less than $1 million. And there's a lot of university projects that are going on, commercial companies that are using smaller satellites. So those satellites are in the order of maybe a handful of $1 million to design and launch and build, which is still a huge capital cost. That's one of the issues with space, is that it's a very expensive space. And in Silicon Valley, they don't like to do hardware, and they don't like to do space because it's so expensive. Now, with some of the OneWeb constellation and Starlink constellation, they're targeting a life of about 5 to 7 years, so they'll be able to replenish the satellites more often, and they're cheaper satellites.
Very good, thank you. The young man has another question for us.
Can't we just recycle the satellites?
I'm sorry?
Can't we just recycle the satellites?
Unfortunately, we can't recycle the satellites. I wish that we could. There are, usually when a satellite is done, if it's in a low Earth orbit satellite, it will actually decay and eventually burn up in space. So everything will burn up in the atmosphere, and there won't be any part of the satellite that comes back down. With the satellites that are very, very far out, one of the things that's actually making them hit their end of life is that they're running out of fuel. So there are some different initiatives that are going on right now around what we call in-orbit servicing, which is where you would have a gas station basically in space and a robotic satellite that would take gas from that gas station and then go to the satellite and refuel it. So the satellite wouldn't have to initially launch with that much fuel, but it would actually get an extension of its life from getting some extra gas.
Very nice, thank you. Another one from the lady.
There's one more question. With so many satellites being launched, are we facing a challenge of managing the space debris?
Yes, yes. Yes, there's actually a lot of initiatives around that. Space is very large, but it's getting very crowded. And when one object goes into another object in space, again, they're traveling 28,000 kilometers per hour. So it creates even more space debris. We've had 2 major collisions of satellites that have happened, and those pieces of debris are still out there. They're still flying around. So there are different initiatives in Europe, in the United States, all over the world to try to mitigate debris. There are concepts of grappling hooks that grab onto a satellite and bring it down to orbit. There are nets and different concepts. But right now, there's international organizations which make sure that everybody's communicating with each other. They know where each other are. No two satellites are able to collide again.
All right, very good. Okay, we'll leave it there. Thank you very much,
Thank you.
Jeanette.